For more than 2 decades, we searched the deepest, most hostile corners of our galaxy for a second Earth. We pointed our most powerful telescopes at alien suns thousands of light years away, assuming that the ultimate prize, a habitable world, must be hidden deep within the cosmic sea. But we were looking in the wrong direction. Right on our doorstep, hiding in the dim glare of our absolute nearest stellar neighbor, a ghost was waiting. An Earth-sized planet closer to us than any other alien world in the entire universe. For years, its discovery remained underrated. Scientists believed this next-door world was nothing more than a scorched, radioactive rock. But a brand new breakthrough has completely shattered that consensus. A hidden defense mechanism buried deep in the data has revealed that this planet isn't just surviving, it's fighting back. This discovery didn't just change what we know about our closest neighbor, it challenged our most fundamental ideas of where life can actually exist. This is the story of the nightmare world next door that just defied the laws of astrophysics. Let's explore Proxima Centauri b and decode the cosmic shield that changes everything. To understand why the latest discoveries about this planet are so fascinating, we have to look at the bizarre layout of the star system it belongs to. From a distance, our nearest stellar destination looks like a brilliant pair of sun-like stars, Alpha Centauri A and B, locked in a tight orbital dance. But drifting far out on the distant edge of their gravity well is a third companion, Proxima Centauri. It's so small, dim and red that it takes a staggering 550,000 years just to make a single orbit around its larger siblings. Nestled deep within the gravity of this tiny star is an alien clockwork of 3 completely different worlds. To truly appreciate this system, you have to understand just how shrunk down it is compared to our own solar system. Take the innermost world, Proxima d. It sits so deep within this system that it's practically skimming the star's surface, completing a full orbit in just 5 days. To put that in perspective, Mercury is the closest planet to our Sun, but Proxima d is more than 10 times closer to its star than Mercury is to ours. It is a completely roasted world of baked rock. Just slightly further out lies our target, Proxima b. It sits squarely in that narrow, shrunk-down habitable zone, orbiting its star in just 11 days. Even though it is incredibly close to a burning star because that star is so cool, the temperatures here could theoretically allow for flowing oceans. It's an Earth-sized world, but its entire cosmic reality is fundamentally compressed. Then, you cross a vast gulf of space to the outer edge of the system. Way out here on the freezing fringes, the faint red starlight barely scratches the dark. This is Proxima c. It's a massive cold super-Earth, locked in a permanent silent ice age, orbiting in total isolation where the star's warmth can no longer reach. When you look at this system as a whole, it's a staggering realization. The entire system is miniature, dense, and hyper-compact, and that extreme compression introduces a critical problem. Because when a planet is forced to exist that close to its star, gravity and radiation change the rules of survival entirely, creating what planetary scientists describe as a bit of a nightmare. Orbiting a red dwarf star comes with a severe gravitational tax. Because Proxima Centauri is so small and cool, Proxima b has to hug its star at a mere fraction of the distance between Earth and the Sun to receive any warmth. At this close range, gravity stops behaving like a gentle orbital anchor and begins to distort the planet physically. This process is called tidal locking. It means that as Proxima b completes its 11-day journey around its star, it rotates exactly once on its axis. The consequences of this synchronization are extreme. One side of the planet is permanently fixed toward the blinding red eye of its sun, condemned to an unending day, while the exact opposite hemisphere is turned away into the freezing vacuum, trapped in an eternal night. A world that doesn't rotate completely breaks the systems of global weather we take for granted on Earth, Without a day and night cycle to distribute heat evenly, the two hemispheres develop wildly different environments. On the day side, the star continually bakes the rocky landscape, driving temperatures upward and drying out any moisture. On the night side, temperatures plunge to near absolute zero. This extreme thermal contrast triggers a phenomenon known as an atmospheric cold trap. Basic physics dictates that hot air rises and cold air sinks. On Proxima b, the air baked by the sun rises and rushes toward the dark side to cool down. However, the night side is so unimaginably cold that as this air arrives, the gases within it begin to rapidly cool and condense. On a planet like this, if the atmosphere contains carbon dioxide or nitrogen, these gases don't just form clouds, they literally freeze out of the sky. They precipitate downward, burying the dark hemisphere under massive silent glaciers of solid nitrogen ice. Over thousands of years, this cold trap acts like a giant atmospheric vacuum cleaner, continually sucking air from the day side and freezing it solid on the night side. Left unchecked, this process can cause total atmospheric collapse, leaving the entire planet as an airless, naked rock. Even if the atmosphere manages to circulate heat well enough to prevent total collapse, it faces a second, much more violent threat from its host star. Red dwarfs are misleading. They look small and weak, but they are actually some of the most volatile magnetic engines in the known universe. Unlike our Sun, which has a stable, layered internal structure, a red dwarf is convective from its core all the way to its surface. Hot plasma constantly wells up from the center, churning the star's magnetic fields into an unstable, tangled web. When these magnetic field lines snap and reconnect, they unleash superflares. Proxima Centauri regularly experiences these eruptions, blasting out solar flares that are orders of magnitude more violent than anything recorded in our solar system. These flares bombard the nearby planets with high-energy X-rays and extreme ultraviolet radiation. Without a powerful defense mechanism, this relentless cosmic bombardment would easily shatter water molecules in the atmosphere, stripping away the hydrogen and bleeding the air into space. For decades, this double trap of tidal locking and brutal stellar flares led the scientific community to a bleak consensus. Proxima b was highly likely a sterile, eroded wasteland. Its close proximity to its sun had sealed its fate, turning our closest candidate for an interstellar home into a dead end. Now let's talk about some of the most recent findings. Breaking a scientific consensus doesn't happen with a sudden visual photograph. We cannot directly see an atmosphere or a magnetic field across 4 light-years of empty space. Instead, changing our understanding of Proxima b required astronomers to play the role of cosmic detectives, analyzing the only clue available to us: the shifting frequencies of the star's own light. A global team of astronomers utilized high-resolution spectrographs to monitor Proxima Centauri over years of intense observation. They weren't looking at the planets themselves, they were tracking the violent flares erupting from the star's surface. Specifically, they were measuring the behavior of certain iron atoms vaporized within the stellar atmosphere during these explosions. The goal was to map the natural, intrinsic rhythm of the star's volatility. But as the data accumulated, a strange pattern began to emerge in the data logs. The star's eruptions weren't entirely random. Something external was subtly manipulating the frequency and intensity of the star's massive magnetic outbursts. When scientists mapped the timing of these stellar flares against the orbital paths of the inner planets, the data lined up perfectly. Many of the star's most violent eruptions were completely phase-locked to the orbit of the innermost planet, Proxima d. As this tiny rock completed its quick 5-day trip around the star, its physical position dictated exactly when the star would experience a magnetic snap. This phenomenon is a direct consequence of star-planet magnetic interaction. It means the planet is orbiting so close to its host that their magnetic fields are literally tangled together. The planet isn't just taking the beating, its own magnetic field is actively carving a path through the star's corona, triggering or suppressing flares as it moves. By calculating the sheer energy required to modulate a star's behavior like this, researchers achieved a historic milestone in astrophysics, the first ever measurement of a terrestrial exoplanet's magnetic strength. The data suggests that Proxima d possesses a polar magnetic field averaging around 16 Gauss. For context, Earth's protective magnetic field is less than 1 Gauss. This tiny baked planet is wrapped in a magnetic shield many times more powerful than our own. While Proxima d is far too hot to maintain life, its massive magnetic shield completely rewrites the survival odds for its neighbor, Proxima b. The same study revealed that the star's flare intensities are also being modulated on an 11-day cycle, matching the exact orbit of Proxima b. The implication is profound. If both of these rocky worlds have generated magnetic fields of this magnitude, they possess a dynamic defense mechanism that changes everything. For a planet like Proxima b, an enormous magnetic shield acts as a deflection canopy. When a violent superflare washes over the orbit, the magnetic field lines catch the high-energy charged particles, forcing them to curve harmlessly around the planet and vent back out into deep space. This changes the primary objection to habitability in red dwarf systems. A powerful magnetic field means that despite billions of years of relentless radiation, Proxima b may have successfully held onto its atmosphere. It is no longer assumed to be just an eroded rock. Our closest cosmic neighbor suddenly stands as a world with a protective shield, preserving whatever environment lies beneath it. With a protective magnetic shield keeping the atmosphere intact, we can finally stop looking at Proxima b as a dead astronomical statistic and start looking at it as an actual place, a physical world with geography, weather patterns, and a landscape shaped by forces entirely alien to Earth. If you were to stand on the surface of Proxima b, the first thing that would break your brain is the sky. Because the planet is tidally locked, the sun never rises, moves, or sets. If you land on the hemisphere facing the star, it sits eternally overhead. If you land on the back, you are marooned in perpetual starlight. But if you travel to the narrow ring dividing these two halves, the Terminator line, you enter a world of permanent, unmoving twilight. Here, Proxima Centauri hangs forever on the horizon, appearing up to 3 times larger in the sky than our sun looks from Earth, bathing the entire landscape in a deep, heavy crimson glow. Because the sun never moves, the climate here is completely static. There are no seasons, no mornings, and no nights. This creates a global weather system that astrobiologists call an eyeball Earth. The permanent dayside acts as a continuous thermal engine, heating the center of the hemisphere and driving massive wind currents directly towards the dark side. At the Terminator line, these opposing forces collide. Cold air rushing back from the dark, icy deserts meets the warm air from the solar side, creating an unending, circling ring of intense wind patterns and permanent cloud cover. Yet, beneath these thick global clouds, this narrow twilight strip is the most hospitable real estate in the solar system's immediate surroundings. It is a region where temperatures could average a mild 0 degrees Celsius. If there is water on this planet, it isn't frozen into the giant nitrogen glaciers of the dark side, nor vaporized by the solar glare of the day side. It pools here in dark, locked oceans that never experience a tide, completely still under a red sky. For nearly a century, humanity looked out into the cosmos and assumed our closest neighbor was a radioactive dead end. The discovery of its powerful magnetic shield doesn't just rewrite the future of Proxima b, it proves that nature has a way of protecting its creations even in the most hostile corners of the universe. We are no longer just wondering if life can survive around a red dwarf star. We are actively planning how to go see it for ourselves. Real-world initiatives like Project Breakthrough Starshot are already designing fleets of microprobes attached to ultralight sails. Propelled by powerful, Earth-based laser arrays, these probes could travel at 20% the speed of light, crossing the vast gulf of space to reach the Proxima system in just over 2 decades. Within our lifetimes, the first data streams and actual photographs of an alien world could be beamed back across the void. And when those images finally arrive, we won't be looking at a barren rock. We will be looking at the crimson shores of a world that fought back against its star. As Proxima b drifts in the permanent shadow of its star, the silence of the cosmos remains. If you want to stay in this void a little longer, the soundscape from today's journey has been expanded into a full 1-hour continuous mix on the Ambient channel. It's paired with a 4K simulation of a black hole sunrise over Earth, designed for studying, sleeping, or just drifting. The link is on your screen right now. Thank you for watching.